Stephen Hawking once said, "The universe doesn't allow perfection." This profound observation would have guided his analysis of one of the most paradoxical scenarios in theoretical physics. What would happen if something as mundane as a sewing needle struck Earth while traveling at the speed of light? While most would focus on the catastrophic destruction, Hawking's genius lay in recognizing that such an impossible event would illuminate the deepest mysteries of space-time, quantum mechanics, and the fundamental limits that govern reality itself. The legendary physicist would have immediately understood that this scenario represents far more than a simple collision problem. It's a window into understanding how the universe prevents certain impossibilities from occurring, how the laws of physics conspire to maintain cosmic order, and what happens when we push the boundaries of theoretical possibility to their absolute breaking point. Hawking's approach would have been uniquely informed by his groundbreaking work on black holes, quantum mechanics, and the nature of space-time. He would have recognized that a light-speed needle doesn't just violate our everyday experience. It challenges the fundamental structure of reality and forces us to confront the most exotic physics imaginable, where the distinction between matter, energy, and space-time itself becomes meaningless. What if I told you that Stephen Hawking's analysis reveals that a light-speed needle wouldn't just create destruction, it would fundamentally violate the causal structure of space-time, potentially create microscopic black holes that evaporate in bursts of Hawking radiation and generate quantum effects so extreme they might literally rewrite the laws of physics in the vicinity of the impact? That such an event might represent the universe's ultimate paradox, where impossible physics creates impossible consequences. This is the story of what Stephen Hawking would have discovered about the ultimate impossible collision, an event that transcends ordinary physics and enters the realm where quantum mechanics, general relativity, and thermodynamics converge in ways that challenge our most fundamental understanding of how reality operates. Before we explore Stephen Hawking's revolutionary analysis of what would happen if a needle struck Earth at light speed and why this impossible scenario reveals the deepest secrets about the nature of space-time and quantum reality, hit that subscribe button because we're about to journey into the most exotic physics imaginable, where everyday objects become windows into the fundamental structure of the universe. Stephen Hawking's approach to this impossible scenario would have begun with his characteristic focus on the fundamental principles that govern space-time and matter. The physicist would have immediately recognized that the premise contains a profound impossibility that reveals important truths about the nature of mass, energy, and the speed of light as the ultimate cosmic speed limit. According to Einstein's special relativity, no object with mass can reach the speed of light, because doing so would require infinite energy. As an object approaches light speed, its relativistic mass increases toward infinity, making further acceleration impossible. But Hawking would have been fascinated by exploring what the physics would look like if we could somehow circumvent this fundamental limitation. The physicist would have started by examining the energy scales involved. A typical sewing needle has a mass of approximately 0.5 grams. At rest, this mass contains about 4.5 x 1013 joules of energy, according to E-hour MC2, equivalent to the energy released by a moderate nuclear weapon. But a needle traveling at light speed would possess infinite kinetic energy, creating a fundamental paradox that would have intrigued Hawking. Hawking would have approached this paradox by considering what happens as the needle approaches light speed asymptotically. As the velocity increases, the needle's relativistic mass grows exponentially, and its gravitational effects become increasingly significant. At velocities very close to light speed, the needle would begin to warp spacetime around it like a microscopic black hole. Think about what this means from Hawking's perspective. The needle wouldn't just be a fast-moving object, it would become a gravitational anomaly that distorts the fabric of spacetime itself. The physicist would have been fascinated by how this transformation reveals the deep connection between mass, energy, and the geometry of spacetime. Recent theoretical work in relativistic physics has explored how ultra-relativistic objects create spacetime distortions that approach the characteristics of black holes. Hawking would have recognized that a light-speed needle represents the ultimate example of this phenomenon, where kinetic energy becomes so extreme that it fundamentally alters the local structure of spacetime. Let me ask you something that would have fascinated Hawking. If a light-speed needle creates spacetime distortions similar to a black hole, what happens to the information it contains when it collides with Earth? Share your thoughts in the comments below, because this question connects to Hawking's famous work on the information paradox and the fundamental nature of information in extreme gravitational fields. Hawking's analysis would have revealed that the needle's approach to Earth would generate gravitational waves of unprecedented intensity. These ripples in space-time would propagate outward at light speed, carrying away enormous amounts of energy and announcing the needle's approach to sensitive gravitational wave detectors around the world. But these wouldn't be ordinary gravitational waves. The extreme energy density of the light-speed needle would create gravitational disturbances so intense that they might approach the Planck scale, the realm where quantum effects become significant in gravitational phenomena. Hawking would have been intrigued by the possibility that such waves might reveal quantum gravitational effects that are normally impossible to observe. The physicist would have also examined the thermodynamic implications of the collision. Hawking's work on black hole thermodynamics revealed that even the most extreme gravitational objects obey the laws of thermodynamics, and he would have applied these insights to understand the energy and entropy changes during the needle's impact. The collision would involve the conversion of infinite kinetic energy into heat, radiation, and exotic matter states. From a thermodynamic perspective, this represents the ultimate irreversible process, where organized motion is converted into the most chaotic possible distribution of energy and matter. Hawking would have been particularly interested in the entropy production during the collision. The needle's impact would create the maximum possible increase in entropy, transforming the ordered structure of both the needle and the impact site into the most disordered state possible. This connects to Hawking's broader work on the arrow of time and the role of entropy in determining the direction of temporal evolution. Recent research in black hole physics has revealed that extreme energy concentrations can create event horizons, boundaries beyond which information cannot escape. Hawking would have speculated that the needle's impact might create temporary event horizons that briefly trap information and energy before evaporating through quantum effects. The physicist would have also explored the quantum mechanical aspects of the collision. Hawking's work on the interface between quantum mechanics and gravity would have informed his analysis of what happens when quantum effects become significant in extreme gravitational fields. At light speed, the needle's de Broglie wavelength would become infinitesimally small, creating quantum effects that operate on scales far below atomic nuclei. The needle would interact with matter at the level of individual quarks and gluons, potentially creating exotic quantum states that don't exist under normal conditions. These quantum interactions would release energies that exceed anything achieved in human-built particle accelerators. The collision might create conditions where the fundamental forces of nature begin to unify, as they did in the first moments after the Big Bang. Hawking would have recognized this as an opportunity to observe physics that normally exists only in the most extreme environments in the universe. The actual moment of impact would involve physics so extreme that our current theories might break down completely. Hawking would have been fascinated by the possibility that such conditions might reveal the quantum nature of gravity, the long-sought theory of quantum gravity that would unify general relativity and quantum mechanics. The impact point would experience energy densities that approach the Planck density, the scale at which quantum effects become significant in gravitational phenomena. At these densities, space-time itself might begin to exhibit quantum properties, fluctuating and foaming at the smallest scales in ways that challenge our classical understanding of geometry. Hawking would have speculated that such extreme conditions might create microscopic black holes that immediately evaporate through the process he discovered, Hawking radiation. These black holes would form and disappear in times measured in units of Planck time, creating intense bursts of radiation that carry away the collision's energy. The Hawking radiation from these microscopic black holes would be unlike anything ever observed. The temperature of the radiation would be inversely proportional to the black hole's mass, meaning that the smallest black holes would emit the hottest radiation. The needle's impact might create the hottest temperatures ever achieved in the universe. Recent theoretical work has suggested that Hawking radiation from microscopic black holes might violate the classical energy conditions that govern normal matter and energy. The radiation might have negative energy density or other exotic properties that could affect the surrounding spacetime in unpredictable ways. Hawking would have also considered the information-theoretic aspects of the collision. His famous work on the black hole information paradox revealed that the destruction of information might be impossible, even under the most extreme conditions. The needle's impact would test this principle to its absolute limits. The collision would destroy not just matter and energy, but also all the information contained in the needle and the impact site. The quantum states of every atom, the precise arrangement of matter, and the complex patterns that define the structure of both objects. According to quantum mechanics, this information cannot be truly destroyed, but where would it go? Hawking would have speculated that the information might be preserved in the quantum correlations of the Hawking radiation emitted during the collision. This radiation might encode all the information about the original needle and impact site in forms that are currently beyond our ability to decode. Recent developments in quantum information theory have revealed that information preservation in black holes might require non-local quantum correlations that span vast distances. The needle's impact might create similar correlations that preserve information in ways that seem to violate our classical understanding of locality and causality. The physicist would have been particularly intrigued by the possibility that the collision might create closed time-like curves, paths through space-time that loop back on themselves, allowing for travel into the past. The extreme space-time curvature near the impact site might create regions where the normal causal structure of space-time breaks down. Such causal violations would create paradoxes that challenge our understanding of free will, determinism, and the nature of time itself. Hawking had previously worked on the chronology protection conjecture, the idea that the laws of physics conspire to prevent paradoxes by making time travel impossible. The needle's impact might test this conjecture under the most extreme conditions imaginable. The aftermath of the collision would involve equally exotic physics. The energy release would create an expanding sphere of destruction that propagates outward at significant fractions of light speed, but this wouldn't be ordinary explosive destruction. It would involve the fundamental transformation of space-time itself. The expanding shock wave would carry with it gravitational disturbances that could affect the orbits of satellites, alter the Earth's rotation, and create tidal effects detectable around the world. But more importantly, it would carry quantum gravitational effects that might reveal the granular structure of space-time at the Planck scale. Hawking would have calculated that the total energy release would exceed Earth's gravitational binding energy by many orders of magnitude. The collision wouldn't just destroy Earth's surface, it would completely disrupt the planet's gravitational field and scatter its mass throughout the solar system. But the destruction would extend far beyond the immediate impact site. The gravitational waves generated by the collision would propagate throughout the universe at light speed, carrying information about the event to distant galaxies and potentially affecting the large-scale structure of space-time itself. Recent observations of gravitational waves from black hole mergers have revealed that such events can be detected across cosmic distances. The needle's impact would generate gravitational waves many orders of magnitude more intense, creating disturbances that would be detectable by any sufficiently advanced civilization anywhere in the observable universe. The electromagnetic effects would be equally extreme. The collision would generate radiation across the entire electromagnetic spectrum, from radio waves to gamma rays, creating a burst of energy that would outshine the sun for brief moments. This electromagnetic signature would announce Earth's destruction to any observers in nearby star systems. Hawking would have also considered the cosmological implications of such an event. The energy release would be comparable to that of supernova or gamma-ray bursts, the most energetic events known in the universe. The needle's impact would essentially create an artificial cosmic catastrophe that rivals the most extreme natural phenomena. The physicist would have been fascinated by how this scenario connects to his work on the early universe and cosmic inflation. The energy densities achieved during the collision would be similar to those that existed in the first moments after the Big Bang, potentially recreating conditions that haven't existed in the universe for billions of years. Such extreme conditions might trigger vacuum phase transitions that could fundamentally alter the laws of physics in the vicinity of the impact. The needle's collision might create a bubble of altered space-time where the fundamental constants of nature take on different values, potentially making the affected region uninhabitable by any known form of matter or energy. Recent theoretical work in cosmology has suggested that vacuum phase transitions might be responsible for cosmic inflation and the creation of multiple universes with different physical laws. The needle's impact might create a miniature version of such transitions, providing insights into the fundamental processes that shaped the early universe. Hawking would have recognized that this scenario represents the ultimate test of our understanding of physics under extreme conditions. The collision would simultaneously involve general relativity, quantum mechanics, thermodynamics, and particle physics at their most extreme limits, potentially revealing new physics that transcends our current theoretical frameworks. The physicist would have been excited by the possibility that such extreme scenarios might provide insights into the theory of everything, the long-sought unified theory that would explain all fundamental forces and particles. The needle's impact might create conditions where the distinctions between different forces break down, revealing the underlying unity of physics. The thought experiment also serves as a probe of the consistency of our physical theories. If our current understanding leads to logical contradictions or impossible consequences when pushed to extremes, this might indicate where new physics is needed to resolve these problems. Recent developments in string theory and quantum gravity have begun to explore physics at the Planck scale, where the effects described in this scenario would become relevant. Hawking would have understood that while we can't perform this experiment, thinking through its implications might guide us toward new theoretical insights. The physicist's analysis would ultimately reveal that a light-speed needle impact represents more than just an impossible collision. It represents a window into the deepest mysteries of physics. The event would create conditions so extreme that they might reveal the quantum nature of space-time, the fundamental limits of information processing, and the ultimate connections between matter, energy, and geometry. Hawking's investigation would show that while such an impact is impossible according to our current understanding, exploring its implications reveals the profound connections between quantum mechanics, gravity, and thermodynamics that point toward a more complete understanding of the universe. The next time you encounter an ordinary sewing needle, remember Stephen Hawking's approach to impossible questions. Sometimes the most profound insights about the nature of reality come from pushing everyday objects to impossible extremes and exploring scenarios that challenge everything we think we know about physics. The universe operates according to principles so deep and subtle that even impossible events can teach us about the fundamental structure of existence. If this exploration of what would happen if a needle hit Earth at light speed has expanded your perspective on the extremes of physics and the nature of space-time, make sure to smash that like button to support more investigations into the deepest mysteries of the universe. Subscribe to our channel and hit that notification bell so you never miss our journeys into the impossible realms where physics reveals its most profound secrets. Share this video with anyone who's ever wondered about the ultimate limits of physical reality, because Hawking's approach to impossible scenarios reveals truths that challenge our deepest assumptions about matter, energy, space, and time. And let me know in the comments, what other impossible physics scenarios would you like to see explored through Hawking's lens? How do you think quantum gravity might change our understanding of such extreme events? What connections between everyday objects and cosmic physics do you find most fascinating? Drop your thoughts below and join our community as we explore the boundaries where the possible meets the impossible and where the deepest mysteries of existence reveal themselves through the most extreme scenarios imaginable.